Hey guys, welcome to video 2. We're going to look at antennas. We're going to look at electromagnetic fields propagating through space. When I say propagating through space, you can see here that at any one point in time, if we were to sit there, we're going to see a difference. And in this particular case, E is representing the electric field. Now the electric field would normally be considered to be voltage. However, I consider the electric field to be current. So I just want people to know that because I set current and magnetic fields side by side. They are one and the same thing. Okay, and when there's a magnetic field, there's a current. Okay, and when there's a current, there's a magnetic field. They are one and the same things. However, voltage can appear and there can be no magnetic field. So voltage is not the magnetic field. Voltage is what can bring on, or at least induce, a current. However, it's not the other way around. Okay, so electric field is considered to be voltage. The magnetic field, which would normally be deemed B. Okay, so this is a confusing diagram. It's a very good diagram, but it is a bit confusing. V, it's a bit confusing because, like I say, that would normally be a B field, magnetic field B, which would normally circle the wire all the way through the wire as the current's moving. Okay, if the current stops moving, then that's no longer a current. And if the current stops moving, then there's no magnetic field. If there's a moving current, which is the definition of a current, if there's charge moving, then there's a magnetic field present. Okay. Time and space. Time and space. Okay, so any time we're in space somewhere, so if we were to sit at this particular point here where the mouse pointer is, just over here, we're just going to sit there. And as time moves on, 1, 2, 3 sort of thing, we are seeing an electric field there, okay, that is changing in time, okay. Now, you could say, if you wanted to, you could say, looking at the wave, looking at how that's propagating, and looking at the direction, okay, of the antenna, remembering an antenna is just a piece of copper, or a piece, doesn't need to be copper, a piece of conducting strip. Okay, it can be anything. It can be aluminium tube, it could be absolutely anything at all, just a piece of copper wire, it could be anything at all. Okay, what we're seeing in point time t is that the wave, the green wave here, is changing and it's propagating at least up and down this wire here, okay, in a very smooth sinusoidal waveform. Okay, so that would be as the current is moving, the electric field moves. Okay, and some will argue that it's the voltage field, but hey, it doesn't really matter, V or I or whatever. And that as the current is changing, then the magnetic field's changing. You've got to remember that magnetic field and the electric field are both the same thing. There's electromagnetic field. And in the ideal conditions, the magnetic field B is at right angles to the electric field E. Okay. Now, again, conductor, conductor, conductor. Okay. A coil is a conductor. An antenna is a conductor. They both have current, or they both can have a current that changes in time. They both have a magnetic field. They both have an electric field. They both can exhibit the electromagnetic field. Okay, so theory would state that a coil is a conductor, antenna is a conductor, so therefore a coil is an antenna. A coil is just an antenna coiled up. Okay, so we still get magnetic field, we still get electric field, we still get everything. We can still put a coil into resonance, whether it be self-resonance or LC or LCR resonance. With the coil itself, a capacitor, and obviously there'd be a resistance involved, which would be the ESR of the capacitor, and obviously the resistance of the coil. Okay, just real quick, I just want to point out, you can see the red here. The red is tuned to a half of the wavelength, okay, and that's what the antenna is tuned to as well. So the length here of the antenna is tuned to a half wavelength to give optimum frequency and resonance at the same time. Okay, so the length of the antenna is important, the frequency is important. The frequency would match the antenna. Obviously the antenna would be brought into resonance. When the antenna is in resonance, the voltage and the current are 90 degrees out of phase. Now, something I missed before I wanted to add in now is the plane. So if you were to sit in a chair and look at an antenna, the plane in which the antenna is put is very important. I've showed some videos in the past that does actually show this already. But the length is important, but also the orientation. So if you were to turn this antenna up long ways, then other receiving antennas on the other end wouldn't work. So if this was the transmitter antenna, okay, and you had another antenna that matched this antenna and was receiving the signal that was generated from this antenna, and if you turn this up long ways, then the other antenna would no longer receive any signal, because the plane in which the E field here is being shown would be different. Okay, so you would have it at 90 degrees compared to the antenna that would be receiving. So 90 degrees would not work, it would no longer work. Also, with the plane, you'll see that the electric field here is flat, if you like, to the coil where the charges are moving. Okay, so as the charges are moving, we see in the plane, in the flat plane of the antenna, we see the difference, okay, in magnitude. Remembering the arrows that are being shown here are direction and magnitude, which is the definition of a vector. So magnitude and direction, the magnitude and direction of that indicate a value, if you like, of the electric field at that point in time in the 3D space, in the three-dimensional space, which would be X, Y, and Z. Okay, so the plane's important, the length is important, and obviously the frequency that the antenna is being driven at or receiving at. Alright, so what we are trying to focus on here is, as the coil comes into resonance, okay, or as the antenna comes into resonance, there's a sinusoidal, electric and magnetic field. Okay, we're going to look at, in a minute, we're going to look at the vectors and show that the vectors are at right angles. And we're going to go into a little bit of detail about this, and then we're going to do some experiments. So I just want to show you this because this is something that's taken me years to learn. I'm not an expert at it. I've learned from some experts, and they would probably no doubt correct me if I've made any mistakes. So I encourage everybody to do their own research as well. But what I'm trying to point out here, and what I'm trying to say, is that an antenna is just the same as a coil. Okay, it's conductive, it has a current, it can be brought into resonance. The magnetic field and the electric field, which then becomes the electromagnetic field, propagates from the coil. It will radiate through space, which we already know to be true. So there really is no difference between an antenna and a coil. Okay, there really is no difference. Okay, so we're going to pause the video, we're going to come back in a sec. Okay, I want to thank Wikipedia for this one. It's a good old Wikipedia image. Again, we can see the electric field here, and we can see the magnetic field. Okay, the magnetic field is greatest at the point where the current is maximum, and it depends where the current is. Sometimes the current might be at the end of the coil up here, or sometimes it might be at this end down here. Okay, so it will, like we just saw, it will move up and down the antenna like this. Okay, we have electric fields which propagate through space with the magnetic fields. Okay, so remembering one is at right angles to the other. So B and E. Okay, E the electric field, B the magnetic field. So electromagnetic field at right angles to each other. Now remember, they're only right angles to each other under certain circumstances. They have to be resonant, they have to be at maximum resonance at 90 degrees, so on and so forth. There's lots of different factors that determine whether they're at 90 degrees, phase shifts, all that sort of thing. Now when we're talking 90 degrees, there's two different parts to that. Okay, so when you're talking LC resonance means that the current is 90 degrees to the voltage. Okay, and that's different. We're talking about a different thing. What we're talking about here is we're talking about the electric field being at 90 degrees to the magnetic field. Okay, now we're not talking about the magnetic field being 90 degrees to the voltage or anything like that. It's the electric field and the magnetic field. Okay. It's worth going to have a quick look online, just sort of do a few research videos on electromagnetism and all that sort of thing, because it may give you a better background, or what I'm trying to explain here might be enough for you anyway. I sometimes do even now, just to sort of refresh and stuff like that, just to double check. Anyway, again, in a resonance system, when we're looking at the voltage and the current being 90 degrees out of phase, that's different. It's a completely different thing. Again, what we're looking at is the electromagnetic field, so B being 90 degrees to E. Okay. Right, we're going to stop the video and just do a little bit more. Alright guys, we're back again. Up here, so magnetic field B, so that's our red arrows. Okay, these are all our red arrows. Up here and down here. Remember, as we go through a cycle, now I should explain at this stage, a cycle refers to a circle. So from here to here, a cycle of what we see on the oscilloscope is just a circle being drawn over time. Okay, a circle it was meant to represent one revolution in the generator back in the old days when they first started sort of going through and documenting and putting this stuff all in the textbooks. So this was meant to represent one revolution of what's called the cycle. So the cycle would be one revolution, and as the magnetic field increases in the generator, we get an increase of amplitude, and then obviously it gets to peak, and then it comes back down to zero over here, and then it comes down to a negative peak and then back up again. Okay, so that would be the that would be a full wave, sinusoidal wave. Okay. Over here, I've just tried recently to document this as the current field. So when I say current field, what I'm trying to sort of say is this is the electric field, but the reason why I'm saying the current field is because this is current and not the voltage. I'll show you the voltage in a minute, and I'll show you why I've been showing it this way. This way is so much easier to understand. If you show it the other way, people get confused. They look at you all strange and think, God, I'm never going to wrap my head around this. So there's a reason why I do what I do. I'm trying to do the best I can. Some people pick on it, but hey, whatever. Now, so current field, you got to think that this is the current in the wire. Okay, so as the current is increasing, okay, current increases, then starts decreasing, comes back to zero, and then starts increasing, and then comes back to zero. Okay. When you have an electromagnetic wave, the electromagnetic wave propagates through space. So this is the direction, the blue arrow is the direction of propagation. Okay, normally, not always, but normally that would be on the x-axis. That's why I've put x up here. and normally x on the Cartesian scale would represent time. Okay, so if you were to sit in a chair still in space, a magnetic field or electromagnetic field would propagate past you and through you, okay, and it would be changing at every point in time. Okay, so for every second, say for example each point here is a second, okay, the magnetic field and the electric field at the same time, okay, remembering they're at right angles, and that's what you see here. They're at right angles, so it would be increasing, 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 and then decreasing, okay, as you were sitting there in time. So each point represents a time marker, so propagation through time. So that's just a single electromagnetic wave, okay, and it's a single electromagnetic wave in one direction. This is the direction it's traveling. Okay, so the antenna might be over here, okay, or coil in our case might be over here, okay, and as we energize the coil, bring the coil into resonance, outward from the coil would be this propagating wave, okay, and sometimes it would be 3D in space, so you'd see it coming out in all directions. Okay, so you've got to remember this is, you could almost say this is even though it's 3D, it's a sort of a 1D representation of what the wave is doing in space and time. Okay, so when I say 1D, it's a 3D diagram, you can see that it's 3D, but at the end of the day it's just representing a very small part of the electromagnetic wave. You've got to remember that it's a 3D structure. It has space, dimension, the time factor obviously to it as well. So, you know, you could say it's got the 4 dimensions at least at the very minimum. Alright, let's pause it and move on to the next one. Alrighty, this is the big one. Okay, again, magnetic field, same as before. Okay, we are saying here B1 plus B2 equals 0. Very, very important. Okay, this equation here is very important. It's going to be something that we're going to see in the future, and if we don't sort of understand it, then it's going to become a problem. Okay, the current field again, we explained that just before. Current I equals 2xi. Okay, in the equations, if you look at the equations, then the current will double if we have a magnetic standing wave. We have 2 directions, we have 2 waves, okay, and the 2 waves are traveling in opposite directions. Okay, so arrow here and arrow here. So one wave traveling up this way with the arrow, the other wave traveling down this way with this arrow. Alright, our magnetic fields, so if we were to start, say at this point, so this magnetic field here, let's say the amplitude of it is 1. Okay, the opposite wave coming through the opposite wave, let's say the amplitude of that is -1. So 1 plus -1 equals 0, which is what we've got up here. So if we were to think about this whole diagram in a form where, hey, hang on a minute, we've got all these magnetic vector B's, the red ones, so for each arrow here it's a vector representing a magnitude and a direction. Each magnitude and each direction would become 0. So effectively what we're seeing here is each one of these red arrows shouldn't be there at all. Okay, it should be 0. We should see no red arrows at all. But the reason I put them there is to show that plus 3 over here, take away plus -3 equals 0. So for each magnetic arrow, it cancels each other out because it's got its opposite here for each one, and each one cancels each other out. So the magnetic field is 0 all the way across this line. Okay, and that's only when we have magnetic fields traveling in opposite directions. Okay, Now I want to pause here for a second, and I want to stop, and I want everybody to think about a generator, an electromagnetic generator, or I want everybody to think about a transformer. Everybody think about an electromagnetic transformer. And every single time there's electromagnetic induction of any kind, we have a standing wave. Okay, at the optimum electromagnetic induction, there's two equal and opposite magnetic fields. So this is always the case. If you do the study, if you look at this, anytime a generator generates a voltage and therefore a current, there's a standing wave in the generator. Okay, the standing wave can vary. So, for example, it might be just a very small current, like the current here might be very small because the magnetic fields might not be perfectly in phase. Okay, so this is 180 degrees out of phase. So you got to remember again, like I was saying before, if it's 1 plus -1, it's 0. But if it's 1 plus -3, so this arrow, let's say the magnetic field is out of phase on one of these phases here. So if it's 1 plus -3, then we end up with, was it, -2. So we're only cancelling 1 out. Okay, and that's why we've got to try and get the out of phase to be 180 degrees out of phase, so we can cancel the magnetic field and get optimum current field. Okay, so this is the current. This is representing the current, because if you represent it as voltage, like some people do, and like theory states that you should, then it's very hard to read the diagram, and I'll show you that again in a minute. So I just want to go through, and I just really want to concentrate on this diagram because it's so important. Again, magnetic fields, the vectors have to cancel. Okay, when the vectors cancel, when they properly cancel and it's all cancelled out, we get a maximum current field, and that doubles according to the average textbook. The current should at least double. We have proven and we've shown in an experiment that it can do much more than double, so it can triple or even quadruple in some cases. It depends. Experiment can change. Various different sort of methods can change this, but science today will tell you that if this is the case, then a standing wave will at least double its amplitude. And you'll remember from the last diagram, if you go back, just skip the video back a bit, the current was only up to here. So the current is now double the amplitude compared to what it was before. So arrow's way out here compared to way up here where it was before. Okay. So current I equals 2 times I. We're at least doubling at the very minimum. We should be doubling. Now if we have different phase angles on the magnetic fields here, then the current can be less. So it might be maybe 1.2 or something like that times I. Okay, so it can vary, but do the experiments and you'll see. So current again will double, okay, but we have to have magnetic fields cancel. Okay, you remember from all the documents, all the Floyd Sweet documents, the whole lot talks about cancelling the magnetic field and all that sort of thing. Well, this is it. This is the electromagnetic wave propagating through space, remembering the directions, okay, remembering that each axis is time, so one moving one way, one moving the other way, okay, and it really is just if you were to think of the axis here as time, one wave you could say would be traveling back in time, even though it's not really. You could say that that's what it's doing, and one wave is traveling forward in time. Okay, and that's part of where Tom Bearden was trying to sort of come out and say, well, energy is part of the time domain, and it is. He is true, but depends on the way that you look at it. Okay, so we're going to pause the video and we'll move on. Alright, again, bathed in simplicity. I just think this is fantastic. There's some pretty cool tools and stuff out there. This is one of them. This is Helix 3D. Use this a fair bit for some stuff. You will love it if you get to use it. Very cool for some things. Okay, so looking at our arrow, you can see that the 90 degrees here is pretty sort of stick it in your face. You know, it's pretty obvious that it's 90 degrees at every single angle that you look. Okay, again, this is the magnetic field B. Okay, again in red. This time what I've done, excuse me, this time what I've done is I've shown the green arrows as voltage. Now you'll see that the green arrows as voltage actually come through at 90 degrees. So when the magnetic field B is at maximum, there is 0 voltage in the system. There is no voltage in the system. Okay, and that's pretty important because you've got to remember our voltage and our current are 90 degrees out of phase. So as voltage is 0, the current would be maximum. So if we were to draw a third wave in here, then we would see that the the current field would be way out here, like we saw before, out to the side, while the magnetic field is at maximum. Okay, now the magnetic field and the current field, there might be a tiny little bit of a delay in there, due to various different things. But at the end of the day, they're pretty much the same thing. It depends on things like your core and all that sort of thing. You know, as excuse me, as time changes, you may see a slight difference in the magnetic field compared to the current. But generally, they're pretty much almost exactly in phase, almost exactly the same in time, and you could plot one against the other and be pretty safe to say that when the current is 0, the magnetic field is going to be 0 at the same time. Alright, so a pretty cool tool to use. Again, the blue arrow indicating the time vector. Okay, vector being a representing direction and magnitude. I try to always sort of say that. Never get it right, however. Anyway, so blue arrow is time, red arrow magnetic field, changing in time. Okay, and green arrow this time voltage. Okay, now again you can probably see why it's very confusing. Not many people will sort of understand, well, why is there nothing here when there's something there? You know, I mean, why is it not? Why is this one way over here and this one way over here? But again, it's because of the resonance. Anytime there's LC resonance in a circuit, voltage and the current will be 90 degrees out of phase. So therefore, 90 degrees for the current would be over here and to over here. So just flip this on its side over here, like we saw before. Alright, so cool stuff. You can play with this all day long. Change the lighting, change the direction, change the whole lot. Very cool. I love it. It's fantastic. Pretty cool stuff. Alright, so I'm going to pause the video. We're going to move on. Alright, you'll remember this from the last video. When we have a double piece of wire, it is almost impossible in any situation when that double piece of wire has ends connected to a load. It's almost impossible to get that piece of wire to have current moving in the opposite direction compared to its neighbor here. So if current was moving down the red wire from the left to the right, it would be almost impossible in most situations to get the current to move from right to left, back this way. What we did a while back, you'll remember, we put a switch in over here to say, right, well, what we want to do is we want to get the current moving in this wire first, and then we're going to put the switch in, and we're going to switch the switch in at a particular time when this wire here will induce a voltage and therefore a current in this wire, which will be equal and opposite and move back the other way. Well, what we just did in the last video is we showed another method, whereas what we can do is get one coil into resonance from a primary coil over here that's off page out of picture. So changing magnetic field off page out of picture, which induces a voltage in one coil which is resonant at a frequency which is different than the frequency on the other coil. So in that case, we measured two different currents, one going one way, one going the other way. One current which was well over double, 2.7 times more in one wire compared to the other wire. Alright. Now, again, we had a few little complaints about that. Someone being picky about how current is currently defined. Look, honestly, I don't care, whatever. I'm going to define current conventionally, the way that most people understand it, the way that science even still today tells people that current moves. I already know that it's wrong, okay, but I'm explaining it the way that most people will understand it. Alright, I'm not going to be picky about it. I couldn't really care less, whatever. Okay, so again, current moving from left to right on the red coil. Our task is to get current to move from right to left on the black coil. Okay, and there's lots of different ways to do it. The switch is one way to do it. Okay, we've got to make things simple so we can understand them properly. And that's what this is really about. This, again, okay, we probably get the same idea here. We are representing this wire here as a primary coil. Okay, so again, the length of the primary coil is being shown. The only difference is that the primary coil is not wrapped up, it's not put onto a core, and it's not looking like it's been put into any service in any sort of transformer or anything. Same again with this one over here. We are representing something a little bit different though. This is our secondary coil. First of all, the length of our secondary coil was a little bit longer, and we're dealing with the same as what we had before. So we've got a length of wire. Okay, it effectively is non-inductive. The way that I'm showing it here at the moment is showing it as non-inductive. So if we were to connect a load to this terminal and that terminal, okay, the induction that would occur, because the way this coil is being represented from the changing magnetic field in this coil over here, the way the induction would occur would be effectively it would be zero. There'd be a very small, tiny voltage there due to imperfections in wire lengths and stuff like that, but effectively the induction would be zero between the two coils. Again, coils are not wrapped up, they're not put onto a transformer or anything like that, but they are pieces of wire that are representing coils. Something that I like to do because it just makes it so much easier to think about it. Okay, so again, primary coil over here, shorter than the secondary coil over here, which is longer. If we were to wrap them up, put them on a transformer, drive the primary coil over here, there'd be no output. We'd get no output because there's no induction. Okay, that's why they call it non-inductive. Now this is a key term. It's a key term because in the past, bucking coils have been thought this way. Okay, this is how bucking coils have been thought of. No, they don't work because they're non-inductive. Bucking coils don't work because you can't induce a voltage in them. And that is entirely true. But what people have completely missed is that just because you can't do it on the first experiment doesn't mean that it can't be done. Okay, this is what people get hung up on. There's been several comments that have been made to me in the past. Oh, your technology doesn't work. I've tried it before and it doesn't work. 100% guaranteed it doesn't work. Well, hey, at the end of the day, they've tried it once, but they've not stopped to think about what they're actually doing and what they need to do. Okay, because I've shown in previous experiments, even though one coil is half the length, I've shown that you can do it, that the currents in this coil, one going one way, one coming back the other way, okay, non-inductive, can be done as long as you think about it properly. Okay, we've got to stop, we've got to think about our experiments, we've got to think about what our goals are, what our objectives are, what we need to do, and we've got to sort of think very hard about how we're going to go about it and how we're going to maximize these very, very simple things. Now, just while we're on this, what I want to do is I want to stop, and we put a question up on the forum not long ago. It was actually about Terrell Capanese's coil, which effectively is a very similar setup to what we're doing here. Okay, we've got a coil that is wrapped so many turns clockwise, so many turns counterclockwise, and we ask the question on how many turns clockwise, how many turns counterclockwise. We'll pause the video for a second and we'll drag that thread up. Alright, it's under magnetic resonance, so what we're going to do is we're going to zip to the bottom of the page there, if we can get there. Okay, here it is here. So this is the coil that I'm talking about. This is Terrell Capanese's aquarium. Okay, and what we want to do is we want to look at this coil and go, okay, well the end of this coil is coming out this way, so we must at least have two layers here in the same direction, because just over here we can see that it starts off and there's no difference in turns. Okay, it comes up here and then it does a backflip on itself, and it actually comes back on itself, which means that there is part of this coil where there are turn for turn. Part of this coil is non-inductive, okay, which is exactly the same as what we're just talking about. Now there's a diagram that's been released, this one here. I don't know who released this. This was put up into one of the forums a little while back. There was a translation. This translation doesn't appear to be correct, so I urge you, if you go through and read this and sort of look at, well, hey, there's turns here, it's got all the measurements, all that sort of thing, just go through, just double check it. Okay, so we don't know for sure that that's the case. Again, I pointed out that this is the case, that where a turn for turn, the magnetic fields that each turn creates when that turn is folded back on itself, turn for turn, that creates a standing wave inside the coil at that particular part of the coil. Okay, and where there is a standing wave, again, current is doubled, the amplitude is doubled in that part of the coil. So we went through that very quickly, got a couple of responses out of it. And I'm just trying to get people to try and think about this, because it is important. It's important that we need to think about now the big problem in a generator, in an electrical generator, the big problem is Lenz's law. The Lenz's law puts a back torque on the shaft, so every foot-pound of torque that you put in on the shaft to turn the generator, there's equal and opposite foot-pound coming back at you that says, no, I don't want to turn. So there's a large amount of resistance, drag, if you want to call it that, on the generator. It doesn't want to turn, and that's obviously our biggest problem. Society needs to overcome Lenz's law. Well, technically it's not actually Lenz's law, but it's the back torque, the current that is in reverse to the torque that is trying to generate it. Lenz's law gives us a negative sign. Negative sign is applied to the voltage and not necessarily the current. Okay, we'll pause the video, go back to our coils. Okay, now again, primary coil, secondary coil. So if we can get a current to flow up the coil, okay, and then a current to flow back down the coil, that means that we have to have a voltage difference from this terminal to that terminal. So somehow we need to induce via our primary coil over here, which is this is the tickling coil, this is the coil that gets the voltage up. And you've got to remember, it doesn't cost anything to get the voltage up. The voltage is free, it's the current is the costing part. That's the MMF, the magnemotive force. Okay, which costs, that's the force part. So force for force, it's equal and opposite force less losses. Okay, that's why we have to overcome the force, drag, negative torque on the generator. So we need a voltage here, okay, and we need a voltage there. So the voltage has to be sufficient that the current will flow. Okay, I equals V over R again. You're sick of me saying it. And then any load that is connected to these coils over here will then light. So bucking coils, bucking coils, bucking coils. Now if you set it really fast, accidentally might be able to slip an F in there, and that would be terrible. We'd have to delete the video. So be very careful when you say bucking coils, because it could work out terribly for everybody. Alright, so again I urge everybody, we are just a simple single thought away of the world's biggest breakthrough, and it's because people in the past have done one experiment and said no, it can't be done. Okay, again, I've had lots of comments, lots of different people have told me no, I've done that experiment and it doesn't work. Well, I'm here to tell you it does work. There's been people before us, lots and lots of different people. It's worked for them because they've managed to think outside the box. And alright, I just want to finish this video off just explaining in this video that I've sent out a public invite to invite Tin Man to the forum. Anybody and everybody is welcome to join my forum. I encourage anybody and everybody that wants to become part of this historical movement, which one day will be historical, will be remembered for a long time to come. So anybody and everybody can come and be a member, but if you come to cause trouble, you will be banned. Okay, troublemakers are not welcome. Troublemakers will be banned. Come distract us, waste time, post spam, anything along those lines, you're going to be banned. Okay, I will warn you, and if you don't abide by the rules, you will be banned. So Tin Man, old mate, even though we haven't seen eye to eye in the past, you are welcome to come and join the forum if you wish. You will be welcome. I will put the differences aside that we have had in the past, and you can come and be part of something better if you want to be. If not, then that's fine. I'm happy with that as well. Okay, last but not least, I want to send out a huge thank you to everybody. Our team is the best team I've ever come across. The plan that I had and have had for quite some time was not to entice people with golden cookies. That's not what I want to do, not what I ever wanted to do. I want people to want to do this. People that want to be able to have an opportunity to make a difference. So this is for all my members. I just want to say a huge thank you. I very, very much appreciate all of you. You're all great people.